We'll discuss now sign convention of shear force. Right. When we are going to calculate shear force value for the given beam, then we can start from the left end to right end, or we can start from to calculate shear force value for each point from right end to left end. You can move from left end to right end or right to left. Right. So, whenever we will calculate shear force, suppose consider here is a point, then we will take a section. Now total beam will be divided into segment. This segment will be known as left segment and this will be known as right segment. During the analysis, all the upward forces on left segment of the beam will be considered as positive and downward forces will be considered negative. In case of right segment, there will be just opposite of left segment. All downward forces will be positive and upward forces will be negative. Do remember, this is not a mandatory case, right? Each book differs with the concept. In some books, there will be a reverse of this. For left segment, they will consider downward forces positive, upward forces negative, and for right segment, downward forces negative and upward forces positive. In your book bank, R.K. Rajput, Strength of Material by Rajput is given. In that book also, reverse is considered. For left segment, they have considered downward positive and upward negative. For right segment, downward negative and upward positive. But here, I am considering upward forces for left segment positive and downward forces for left segment negative. And for right segment, upward forces negative and downward forces positive. This is all about the sign convention for shear force, right? Now discuss shear force diagram. In case of shear force diagram, the value of shear force for each point will be denoted on ordinate and position of cross sections will be mentioned on abscissa. This will, here we will graph position of section, that is position of cross section for the points, and for each point corresponding shear force will be located on ordinate, right? So when we'll map, suppose this is a given reference line for this point. For this point, shear force value is here something. This is of amount W1, and for this point it is W2, and variation between these two loading region is if beam is subjected between these 2 points, a point load, then say it is subjected to a UDL between this point, then the graph will be or inclined line like this one. So this variation is showing that between these two load point, shear force is being varied by a inclined line. There is really a relationship between these two load point. Further we will discuss in detail by considering example. So this is all about shear force sign convention and shear force diagram. Now come to the bending moment. This is also an internal resisting moment set up against the bending moment, right? And they also have their negative and positive value for their sign convention, right? So consider a beam. AB. When it is subjected to external moment, either it will bend like this one, and either it will bend upside like this. We'll discuss each case in detail. First, define what is bending moment. Bending like this way is the external effect of the beam. But what will be the internal effect? Beam itself will resist this external bending. Suppose if beam is bending like this, then the resistance bending moment will be set up in this way, and for this one in this way. We can say bending moment, it is the bending moment, it is internal resisting moment set up by beam itself against external bending. Sometimes people refer beam set up against the bending moment set up against the bending is basically bending moment. So it is internal resisting moment set up against by beam itself against external bending. So it can be written as, for the equilibrium of beam, internal external moment minus internal resisting moment equal to क्या होना चाहिए? 0. So we can write internal resisting moment equal to external moment. Or it can be written as, for internal resisting moment we can write bending moment equal to, and in place of external moment we can write sigma m or sigma Fyi di. So this is a mathematical expression for bending moment. Now sign convention. For bending moment, sign convention of bending moment, they are also negative and positive. Negative bending moment is known as hogging bending moment, and positive bending moment known as sagging bending moment. So first of all, we will discuss positive bending moment or sagging bending moment. In case of sagging bending moment, So this is beam AB, beam bend like this way. The sagging bending moment always causes concavity in upward directions, in upward fiber of the beam, right? And in this case, beam bending moment for left segment, this is your left segment and this is right segment. When we are moving for the analysis from left into right hand, then this moment, this arrow, when we will complete this arrow, there will be symbol like this way, clockwise. The clockwise moment is positive for left segment, and similarly when we complete this curvature, there will be anti-clockwise rotation. Anti-clockwise rotation for right segment is positive. Finally, if we analyze this one by forces, then for left segment, upward force will cause clockwise movement, and for right segment, upward force here, the same effect they will generate, upward force here cause anti-clockwise movement. So we can say bending moment for all upward forces is positive. General, indicating that means bending moment for all downward forces is negative. So we can say bending moment for all upward forces is positive irrespective of the segment we have chosen for the analysis. Generally, sagging occurs in case of simply supported beam. Usually, sagging occurs in case of simply supported beam. Now negative bending moment, also known as hogging bending moment. Here beam bend in upward direction, resting moment will come like this. When we will complete the arrow, the curvature, here will be anti-clockwise and here will be clockwise rotation. So for left segment, anti-clockwise will be negative, and for right segment, clockwise will be negative. And this will be true for all downward forces. So we can say bending moment for all downward forces is negative irrespective of the segment we have chosen for analysis. Now bending moment diagram. In bending moment diagram, position of cross section will be located on abscissa and bending moment value will be mapped on y-axis, and for given load points we will draw the variation as we have discussed in CF force. And detail, we will discuss the variation in the numerical and for different condition of the beam. Right? So this is all about CF force and bending moment. Now, come to the problem. We will calculate CF force and bending moment value for the statically determinate beam. So consider a problem, right? Suppose problem is given like draw SFT and BMD for simply supported beam subjected to center load. Right? I think when such a problem is given, then now this problem shows that there should be a procedure, a written procedure for the calculation. How should we go from a given loading diagram to CF force value, bending moment value? So I would like to, before solving this question, I would like to recite you the procedure which we opt, say step which we opt for the analysis of CF force and bending moment diagram. So you can write a step to draw SFT and BMD. Let's recite it quickly so that after we will come to the problem. First, draw loading diagram. Draw loading diagram of given problem. Second, calculate or find CF force value, shear force R. Okay, first comes shear force value for each section of the beam. And then for each point of the beam, each load point, and then for each load point of the beam. This special case, if shear force is being 0 for a given section, if shear force is being 0 for a given section, then calculate zero shear force point for that section. Why? Because further in derivation will show you that for in a given section at 0 shear force point, bending moment is always maximum. So it is required, if in a given section shear force is being 0, then calculate 0 shear force point for that section. And third step is calculate bending moment value for each section and then for each point, each load point, then for each load point of the beam. And then some special cases, here is 2. If CF force is being 0, for a given section, then calculate maximum bending moment value for this 0 shear force point. And second sub case is if bending moment is being 0 for a given section, then calculate position of the point where bending moment is being 0. Moment is being 0 for a given section, then calculate position of the point where bending moment is being 0. This point is also known as point of contraflexion and is also defined as the point at which bending moment curve changes its sign for a given section, right? Change its sign for a given section means 0 will be a reference point. Up to the 0, it will be on positive side, and down to the 0, it will be on negative side. So sometimes people also define it as the point at which bending moment curve changes its signs. So this point is known as point of contraflexion. So these 3 steps are required for drawing shear force diagram and bending moment diagram for the beam. So now come to the problem. Problem was draw SFD and BMD for simply supported beam subjected to central load W. Right? We are saying it central load W. So say it is of magnitude W Newton, and this is our beam AB. Length is L. Load is acting at center, so this length will be L by 2. Right? And this is the loading diagram of this given problem. Now stepwise, first step was to draw loading diagram of given problem. Now it is completed. Come to the second step. Now we have to calculate shear force value for each section, right? So A, B, one thing we have left, I think so. After first step, draw loading diagram of given problem. We should have the value of load at each point. So it is simply supported. Then here will be reaction A and here B, RA and RB, and value of RA will be, for this case, W by 2, and here it will be W by 2. So this is actual loading diagram, not is completed. This is the loading diagram of given problem, right? Now we will calculate the shear force value for this problem. Consider we are moving from left end to right end, and there are 3 load point A, B, and this is C. So consider one section AC, or we can say when we will move from one end to another end, from left end to right end, then it start move from A to C. So we will not go to exactly at C, just left of C, right? Just left of C. And distance of this cross section is X, right? C pointed just right of it. Why we are considering just left of C? Because we will calculate the value of shear force, या internal resisting effect, for this load W by 2 just left of C. Because of this load is being added, the effect of these two will start from C to left of B, right? But effect of load RA, W by 2, is starting from A to left of C, right? So we are considering first segment just left of C. So this is our left segment, because we are moving from left to right. So sign convention of left segment will be applied for shear force and bending moment. Clear? So with the mathematical formula of shear force, we know that shear force for this segment Fx will be algebraic sum of all the forces, all vertical forces acting on this segment. So for x length of beam, the vertical forces are only one. There is one vertical force, that is W by 2, and it is in upward direction, so it is positive. W by 2. Already we have covered sign convention. In sign convention, when we are considering left segment, upward forces are positive, right? Fx equal to W by 2. Now, this W by 2, this expression is independent of x. It does not depend on the position of cross section, but we can write here x to the power 0. Also, this force is being represented on y axis, so similarly we can compare it, make analogy. Fx is represented on y axis and W by t is constant, y equal to c. What it is showing? It is the equation of a line parallel to x-axis at distance of c, right? So this is the shear force value for the section A to C. In a second step, we have mentioned calculate shear force value for each section of the beam. So for first section, this is the value of shear force, and variation is a constant line, because this equation is analogous with a line parallel to x-axis, right? Now we can say we are moving from left to right. So for point A, the value of x is 0, and segment is here just left of C. So for x equal to L by 2 at point C, for x equal to 0, Fa equal to W by 2, and for x equal to L by 2, Fc equal to W by 2. This is x independent, y equal to c. Here it is showing this is equation for a constant line or parallel line. ठीक है, right? So now the shear force value for two load points is known for A to C. Now come to next section. Next section is C to B for segment CB. This is for AC. Now come to CB. When we are moving from C to B, right, the effect of these two forces are up to the point B. Not exactly at point B, it will be just left of B, right? Here it is shaded, W, here W by 2, and this distance will be now X. In some book, distance X is measured from this point, right? Here it is X, and they will minus, for this length, they will minus this length from the X. That means they will consider this effective length of analysis X minus L by 2, but here for the ease of calculation I have considered from C as for the analysis of the length analysis required length of the analysis will remain X, right? So for this case, shear force will be Fx equal to upward forces. Total analysis length of analysis for this case will be L by 2 plus X, right? L by 2 plus X. So Fx equal to W by 2 upward and W downward. So it is negative. The Fx equal to will be minus W by 2. It is also X independent. Directly we can write Fc equal to minus W by 2 for X equal to 0 and Fb equal to W minus W by 2 for X equal to L. For X equal to L by 2. Right? For X equal to L by 2. So in this way, both sections are completed, both segments are completed. Now we can draw the SFD of the beam. This is your length. This is point A. At point A, the value of shear force is W by 2. At point C, it is again W by 2. Variation for this one, Y equal to C, constant line, right? So we'll make a constant line here. Now, for point C, it is minus W by 2. At this point, at point C, here it is in upward direction, downward direction, within we will make a line, right? And for B, it is minus W by 2 again, and equation is independent of X. Here will also be a constant line, and at the end of the section, shear force is always being 0. So we will make a closed curve. This is required shear force diagram for a simply supported beam subjected to center load. Right? Now we will make a bending moment by diagram for the same problem. This is your problem. This was our shear force diagram. Now I have to make a bending moment diagram for this section. Right? This is L by 2, and reaction is W by 2 and W by 2. This is point B, C and A. For bending moment, for first section is AC. So for this segment, here will be a segment. For first problem I am making each diagram of each segment, but after that I will make the section cross section diagram in the given problem, right? W by 2, and here is the section, this distance is x. Now there is only one force, I have to take the moment of this force about this cross section, and this is upwards force, then moment of this force is positive, then bending moment for this section is W by 2 into x. Here the power of x is 1, and it is analogous with the equation y equal to mx, that is the equation of an inclined line, right? So this is the bending moment value for a given section. Now we will calculate the bending moment value for each point covered in this section. So covered point in this section are A and C. For x equal to 0, point is MA, and bending moment value for at point A is 0, and second point is C, and for this point x equal to L by 2, and bending moment value for this point is W by 2 into L by 2, WL by 4, right? Now come to second segment. Second segment is CB. Again make a diagram. W by 2, here is W, and this is the section. Here is the length x. Length of analysis is L by 2 plus x. Write the equation mx equal to W by 2 into L by 2 plus x. This is upward force, so this is positive, and for W is downward, then bending moment of this force W about this section is negative, that is W into x. For this L by 2 plus x, for this section covered points are C and B. For C x is 0, for C x is 0, and for B x equal to L by 2. Put this value into these equations. So MC equal to W by 2 into L by 2 plus L by 2, L by 2 plus 0 minus 0, it is WL by 4. And for point D, when we will calculate, we will see that value is being 0, because it is mentioned when we will move from right to left, then this will be first point, and from here, then it is first point, then x equal to 0 will be here when we will move from right to left, from B to A, then for point B, MB equal to 0. So it is always noted point that bending moment for start point of the beam, either we are moving from left to right or right to left, when it is a load point, is always 0. In a particular case, when external moment is given at a start point, then bending moment is not 0. But whenever it is a load point, then bending moment for the start points is always 0, right? Now we'll draw the bending moment diagram. Come from this section. For point A, M equal to 0, and for point C, value is WL by 4. So this is point A and this is point C here. Now variation for this section, variation is y equal to mx, that is an inclined line, so we will make a inclined line. Now for section CB, value at point C is WL by 4, it remained WL by 4, and for B is 0. Again here the power of x is 1. This is the equation of inclined line, so this is WL by 4. So this is required bending moment diagram for simply supported beam subjected to center load, right? So that's all. Further we will discuss a second problem when beam is subjected to uniformly distributed load.